In previous video, we discussed about the temperature distribution in many geometries. First, in flow between two parallel plates, in pipe, and now we discuss about the temperature distribution between two concentric rotating cylinders. In this figure, this is the figure in which this is the figure. Let us consider the flow between two concentric rotating cylinders, assuming that z-axis is along the common axis of the cylinder and r denotes the radial distance outward from the z-axis. In this case, the non-zero component of velocity is v theta and there is no pressure gradient in theta direction. And velocity distribution v theta is equal to 1 upon r2 square minus r1 square into omega 2 r2 square minus omega 1 r1 square minus omega 2 minus omega 1 r1 square r2 square upon r का whole square. This is diagram. Inner cylinder radius is r1, outer cylinder radius is r2, and angular velocity in the cylinder is omega 1 and and outer cylinder angular velocity is omega 2. And in this figure we clearly it is also shown that non-zero component of velocity vz. This in this diagram v theta, this is shows the flow pattern in the this situation. Now the equation of steady now the equation of energy for steady flow of a viscous incompressive fluid between two concentric rotating cylinder without addition of external heat in cylindrical polar coordinate reduces to 0 is equal to kappa into 1 by r d by dt into r into capital D by dt upon dr plus mu r d upon dr of v theta by r square. This is our equation number 1. And the boundary conditions are when r is equal to r1 temperature T is equal to T1, and when r is equal to r2 then temperature T is equal to T2. So now for the flow between two concentric cylinder, velocity distribution is given by v theta is equal to 1 upon r2 square minus r1 square into omega 2 r2 square minus omega 1 r1 square into small r minus omega 2 minus omega 1 into r1 square into r2 square upon r. This is our equation number 3, where r1 omega 1 and r2 omega 2 be the radius and angular velocity of the inner and of the outer cylinder respectively. Put value of 3 in equation number 1. Then we get 0 is equal to kappa upon r into d by dt of small r into d by dr of capital T plus 4 mu omega 2 minus omega 1 square into r1 की पावर 4 into r2 की पावर 4 upon r2 square minus r1 square into 1 by r की पावर 4, और d by dt of r into d by dr of capital T is equal to minus 4 mu upon k into omega 2 minus omega 1 square r1 की पावर 4 into r2 की पावर 4 upon r2 square minus r1 square का whole square into 1 by r cube. This is our equation number 4. Integrating equation 4 with respect to r, then r into d by dr of capital T is equal to twice mu upon k into omega 2 minus omega 1 square into r1 की पावर 4 into r2 की पावर 4 upon r2 square minus r1 square into 1 by r square plus constant of integration a. Then divided by r, then again we get d by dr of capital T is equal to twice mu upon kappa into omega 2 minus omega 1 square r1 की पावर 4 into r2 की पावर 4 upon r2 square minus r1 square का whole square into 1 by r cube plus a by r. Again integrate it, then we get capital T is equal to minus mu by kappa into omega 2 minus omega 1 square into r1 की पावर 4 into r2 की पावर 4 upon r2 square minus r1 square into 1 by r square plus a log r plus b. This is our equation number 5. So the temperature in given by the relation 5. Applying the boundary condition 2 in the equation 5, then we get T minus T1 upon T2 minus T1 is equal to n into r square minus r1 square into r2 square upon r2 square minus r1 square into r square plus 1 by n into log of r upon r1 upon log of r2 upon r1. This is our equation number 6. In this equation, T1 and T2 are the temperature when the radius is r1 and r2, T is temperature, and n is equal to mu into omega 2 minus omega 1 square into r1 square r2 square upon kappa r2 square minus r1 square into T2 minus T1, where kappa is thermal conductivity, omega is angular velocity of the inner cylinder, omega 2 is the angular velocity of the outer cylinder, r1 is the radius of inner cylinder, and r2 is the radius of outer cylinder. And this capital N is known as non-dimensional parameter. And this equation 6 shows the required result on the temperature distribution between two concentric rotating cylinder. So we can find out the temperature distribution between two concentric rotating cylinder by the equation number 6. Thanks.